Hi everyone, I am Whit Roy. Today, I invited electrical tutor Mark to review apprentice Sarah's electrical protection test paper. First, I will show all the test questions on the screen. You can have a try yourself, then Mark will go through Sarah's paper. For each question, tutor will explain why the correct answer is right and why the other options are wrong. I hope you enjoy this style of learning. First, let's start this electrical protection test. 3, 2, 1, go. Now, let's review this electrical protection test. 3, 2, 1, go.
Question 47. Regarding operation of an RCD, which statements are correct?
I know an RCD is something to do with shock protection, but I still mix it up with overload sometimes.
Good, let's sort that out properly. An RCD works by comparing the current going out on the active with the current coming back on the neutral.
So it's checking whether the current going out matches the current coming back?
Exactly. In a healthy circuit, the current leaving on the active should return on the neutral. If those two are equal, the RCD sees balance and does nothing.
And if they're not equal?
Then some current is going somewhere else, often to earth, possibly through a person, damaged insulation, or an unintended path. That difference is called residual current or imbalance current.
So the correct ideas are that it detects imbalance, it trips when residual current exceeds the rating, and it provides additional protection against electric shock.
Exactly. Now, the wrong one says it operates based on overcurrent only. That is wrong because an RCD is not an overcurrent device. It does not measure total load current in the same way a fuse or circuit breaker does. It measures imbalance.
So if I have a perfectly balanced heavy load, an RCD might not trip at all.
Correct. Heavy load alone does not make an RCD trip unless there is imbalance. Question 48. Which conditions will cause an RCD to trip?
Leakage current to earth, I think?
Yes, that's one. Let's build the whole picture. If current leaks to earth, then current leaving on the active is no longer equal to current returning on the neutral. That imbalance is what the RCD detects.
So it doesn't matter exactly where the current goes, as long as it doesn't return normally.
Correct. That's why fault current flowing through an unintended path is also right. Also, if insulation fails and allows current to leak somewhere it should not, that again creates imbalance.
So all those are really different examples of the same basic principle.
Exactly. That's the deeper understanding. They all cause current to leave the intended circuit path.
And balanced load current is wrong because balanced means equal out and back.
Yes, balanced current is normal operation. No imbalance, no trip. Question 50. What does an RCD not protect against?
This one always gets me. I think overload and short circuit.
Yes, and let's be really clear here. An RCD is for residual current imbalance. It is not there to protect conductors from overheating caused by overload. It is not there to clear a high short circuit current as the primary fault protection.
So if a cable is overloaded but all the current still returns through neutral, the RCD won't see anything wrong.
Exactly right. That's the cause and effect. Too much current, but balanced current, means no residual imbalance, so the RCD may stay on while the cable overheats.
That's why we still need fuses or circuit breakers.
Yes, they deal with overcurrent. The RCD deals with imbalance. The option saying earth leakage faults is wrong because that is exactly what RCDs are intended to respond to. Question 50. Which situations may result in nuisance tripping of an RCD?
Leakage currents from lots of circuits, I think?
Yes, let's go deeper. A single device may only leak a tiny amount of current to earth, not enough to trip an RCD. But if several devices are on the same RCD, those little leakage currents can add together.
So even though nothing is badly faulty, the total leakage may still reach the trip point.
Exactly. That's one common reason. Another is transient voltages during switching. Sudden switching, especially with inductive or electronic loads, can produce brief effects that disturb the circuit and lead to nuisance tripping.
And long cable runs with capacitive leakage.
Yes, long cables can have capacitance to earth, and that can create leakage current effects. So again, the RCD may trip even though there isn't a dangerous permanent fault.
So balanced resistive loads are wrong because they don't create imbalance.
Correct. A normal balanced heater load, for example, would not be expected to cause nuisance tripping just by being resistive and balanced. Question 51. RCD sensitivity ratings.
Lower rated current means more sensitive?
Yes. For example, a 10 milliamp device is more sensitive than a 30 milliamp device because it trips at a lower imbalance current.
Wait, before I answer, what exactly does sensitivity rating mean in the question?
Good question. In this question, sensitivity rating means the rated residual operating current. That is the level at which the RCD is designed to trip. It is not the exact trip value, but the rated level.
So if it says 30 milliamp, it doesn't mean it always trips exactly at 30.
Correct. A 30 milliamp RCD can trip a bit lower, like mid-20s milliamp, and that is still normal. The number is a rating, not an exact trip point.
Got it. So smaller number means it reacts earlier.
Exactly. That's why lower rated current means higher sensitivity.
And 30 milliamp is common for personal protection.
Yes, that's the typical figure people remember for protecting people from electric shock.
What about higher values like 100 or 300 milliamp?
Those are less sensitive. They allow more leakage before tripping, so they are usually used for equipment protection or to avoid nuisance tripping.
So sensitivity rating doesn't tell you supply voltage.
Exactly. That wrong option is there to catch someone who sees a number and assumes it must mean voltage, but the sensitivity rating is about residual current, not supply voltage. Question 52. What conditions must exist for an RCD to operate correctly?
Current must return through neutral, and there must be imbalance?
Yes, let's explain that carefully. The RCD monitors the active and neutral conductors passing through it. Under normal conditions, the current leaving and returning are equal.
So it's really comparing those two currents.
Correct. For tripping to occur, some current must leave the intended path and not return through the neutral conductor in the normal way. That is why the option about fault current flowing outside the intended circuit path is also correct.
So why is voltage must exceed rated wrong?
Because RCD operation is not based on supply voltage exceeding some threshold, it is based on current imbalance. People often confuse voltage problems and protection problems, but this one is about imbalance current. Question 53. Characteristics of overcurrent protection devices.
They protect against overload and short circuit?
Yes, that is the core idea. Let's connect the logic. If too much current flows for too long, conductors heat up. Overcurrent devices interrupt that current before damage becomes severe.
So they protect the cable and the equipment from overheating.
Exactly. They also limit fault current duration by opening the circuit quickly. Not necessarily by reducing the instantaneous current value itself, but by cutting the time the fault is allowed to continue.
And they do not detect imbalance currents.
Correct. That's the RCD's job, not the overcurrent device's job. Question 54. Which devices provide overcurrent protection?
Fuses and circuit breakers?
Correct. A fuse melts when current exceeds a certain level for long enough or during a major fault. A circuit breaker trips open.
Why is RCD only wrong?
Because an RCD may not respond at all to a balanced overload, so it is not an overcurrent protection device by itself. And an isolator is only for switching and isolation, not automatic fault protection. Question 55. What determines correct selection of a circuit breaker?
Prospective fault current and cable current capacity?
Yes, and also load characteristics. Let's unpack that. Prospective fault current matters because the breaker must be able to safely interrupt the maximum fault current that could occur at that point.
So if the fault current is higher than the breaker can handle, that's dangerous.
Exactly. Cable current carrying capacity matters because the breaker must protect the cable. If the breaker rating is too high for the cable may overheat before the breaker trips.
And load characteristics.
Yes, some loads like motors have high starting current, so you choose a breaker characteristic that allows normal starting but still gives protection.
So color of insulation is obviously not relevant.
Correct. Question 56. Short circuit conditions.
Very high current flows?
Yes, that's the starting point. A short circuit means a very low resistance path, so current rises sharply.
And that causes heat.
Rapid heat, yes, and sometimes arc energy as well. That is why protective devices must operate quickly. The wrong option, saying voltage increases across the circuit, is not the correct description here. The main danger is very high fault current and its heating and destructive effects.
So short circuit is not just a fault, it's a very severe low impedance fault.
Exactly. Question 57. Discrimination between protective devices.
I remember this one a bit. Only the nearest device should trip?
Yes, that's the main goal. Let's say there is a fault on one branch circuit. Ideally, only the device protecting that branch should trip, and the rest of the installation should stay energized.
So the upstream device stays on.
Yes, if proper coordination exists. That is why upstream devices remain operational during faults is correct, in the sense that they should not trip for a downstream fault if discrimination is correct.
And coordination between devices is required.
Exactly. Discrimination doesn't happen by luck. Ratings and characteristics must be selected properly. All devices trip simultaneously is the opposite of good discrimination. Question 58. Which conditions increase prospective fault current?
Low circuit impedance?
Yes, the lower the impedance, the higher the fault current. That's a very important relationship.
So shorter cable length also matters because shorter cable means less resistance.
Exactly. Shorter length generally means lower impedance, so the fault current can be higher.
And high supply capacity.
Yes, a strong supply source can deliver a larger fault current. High resistance connections are wrong because they actually limit current rather than increase it.
So this question is really all about what makes the fault path easier for current to flow.
Perfect. That is exactly the right way to think about it. Question 59. Earth fault conditions.
Fault current flows to Earth?
Yes. An earth fault means current leaves the intended path and goes to earth or to exposed conductive parts connected to earth.
So touch voltage may be present because metal parts can rise above earth potential.
Correct. That's the danger. If a person touches a live faulty metal part and earth, current may pass through the body.
So protective devices must disconnect supply.
Exactly. That is the purpose of earthing and protection working together. Circuit remains balanced is wrong because an earth fault usually creates imbalance and abnormal current paths.
So earthing helps the breaker or fuse do its job.
Exactly. That is why earthing helps the fault clear quickly, and by keeping exposed metal parts closer to earth potential, earthing helps reduce touch voltage risk.
It definitely does not increase system voltage.
Correct. Question 60. What functions are provided by earthing systems?
Low impedance path for fault current?
Yes, that's one of the most important. Earthing provides a path that allows fault current to flow strongly enough for the protective device to operate.
So earthing helps the breaker or fuse do its job.
Exactly. That is why assist operation of protective devices is correct. Also, by helping faults clear quickly and by keeping exposed metal parts closer to earth potential, earthing helps reduce touch voltage risk.
It definitely does not increase system voltage.
Correct. Question 61. Which conditions may lead to failure of protective device operation?
High circuit impedance and poor earthing?
Yes, and also incorrect device selection. Let's link those properly. If circuit impedance is too high, fault current may be too low to trip the device quickly.
So the fault is there, but not enough current flows to force disconnection.
Exactly. Poor earthing connection creates the same kind of problem. Fault current path becomes weak or unreliable.
And wrong device selection means even if the fault current is there, the device may still not operate as needed.
Yes, it may be rated too high or have the wrong characteristic. Balanced load conditions are wrong because balanced normal load does not explain failure of protective device operation. Question 62. Safe isolation procedures.
Supply must be isolated, tested, and locked and tagged.
Yes, let's go through why each one matters. First, isolate the supply. That removes the normal source of danger. Then verify isolation by testing. That is critical because you must not assume isolation is effective just because a switch was operated.
So testing confirms it is actually dead.
Exactly. Then lock and tag. Locking prevents accidental re-energization. Tagging warns others that work is being carried out and the circuit must not be restored.
So live testing is always preferred is wrong because safe isolation is the normal safe approach before work.
Correct. Live work is not the preferred default. Safe isolation is.
Yeah, this section really does need more explanation. If I only remember one sentence, I can still choose the wrong answer.
That's exactly right. Protection questions are often about sequence and consequence. For example, imbalance causes RCD tripping, low impedance increases fault current, poor earthing weakens fault clearing, and incorrect device choice affects safety.
So the exam is checking whether I understand what happens next.
Yes, that is why cause and effect matters so much in protection.
This helped a lot more than just hearing the correct option.
Good, that's the point. Once you understand the chain, the answers become much clearer.